This will be the third lecture of the course Introduction to Computing, CSC 101. So I'll start off with the review of the last lecture, where we spoke about complexity. Okay, so we were talking about the linear search, and we said that the best time that it takes is one iteration. The worst case is n iterations, average was n upon 2. And so we gave the notation order of n, all right? Now notice that when I've got an R written over here, this is a revision slide. I hope that's clear by now. Then we looked at Python programming last time, and we looked at simple print statements. We looked at how to define variables. We also looked at the if conditional statement. And next, we also looked at iterations. So this was an example where we did a loop for n ranging from 1 till 2. It would print out something, okay? Similarly, over here, this was an example where it was downwardly, it was decrementing instead of incrementing I. Now, we looked at the example of an unsorted search. And basically, at the end of this, we realized that this wasn't a very efficient way of doing a search if you have an unordered list, okay? And so the question now is, how bad is this algorithm? How good is this algorithm, right? So the way to address this is by looking at the time complexity. So we've already introduced the notation of order of n, and now I'm going to give a little bit more details as to what that means. So if you look at the time complexity, order of n, if, for example, your time complexity is taking a time, let's say t is the number of seconds your algorithm is running for, and if somehow you know the equation for it, and it is given by, for example, 100 times n plus 25. Okay, so there's a constant over here, and you have 100 multiplied by the number of the number of the size of your list. Okay, so in this case, we will refer to this as order of n. So this is referred to as the big O notation. Okay, is there a question, Josefa? Is there a question? If you have a question, as I said, please speak your name first and then go ahead. Okay. If you don't speak your name first, I will generally ignore you. So the question is, why is this order of n, okay, and not, for example, order of 25 or something? Well, the basic way that you determine the order is you let n go to infinity, okay? And as n goes to infinity, the highest power of n dominates the expression, okay? So as n goes to infinity over here, we will say n going to infinity. You can basically see that 100 times n is the term which will dominate this expression, okay? And this will become much larger than the number 25. So 25 will become negligible. For example, if n is 1,000, this will become 100,000, and so the number 25 will become negligible, right? So what is left is basically 100n, and then we're not going to look at the constants associated with n, okay? So for example, the expression could be alpha n plus beta. This would be referred to as order of n, okay? So let's take a look at another example. So the next example is, let's say the time taken, somehow we figured out the expression is 3n squared plus 5n plus 20. So in that case, this would be referred to as order of n squared. Why? Again, because as n goes to infinity, these terms become very small or negligible. And so this term dominates, and we simply drop the constant over here, and we refer to this as order of n squared. All right. So similarly, here's another example: 2n to the power 4 times plus 5n cubed plus 200n squared plus 10,000. So clearly, the highest power of n is n to the power 4, and so this will be referred to as n to the power 4. Okay. What happens when the expression doesn't, the time doesn't depend on n? Okay. If, for example, if it is 500 or whatever, but it's a constant, it doesn't depend on n, then we simply refer to this as order of 1. Okay, so I hope that is clear to everybody. Is there any questions? Please let me know. Otherwise,
Sir, my name is Saira Batul. I have a question. Like here it is written is n is greater than infinity. Is it minus?
No, this is a
Beside
term
n?
which is n approaching infinity. So n, when you have an arrow going to infinity, this means that
Okay.
n becomes larger and larger and larger. Okay, so I've simply written it
Okay,
as
sir.
n and an arrow. Okay,
Okay, sir. Got it.
yeah. So,
Nafisa Hassan,
Ji Nafisa, Ji.
I have a question. This worst case is equals to n iterations. Sir, can you please
Okay, so this is from the previous session lectures. If you look at, for example, what's the worst case scenario in this, if you look at, for example, in this case, what's the best case scenario? Okay, the best case scenario is that you start off with I is equal to 0, and the number that you're looking for is right over here. Okay, so the worst case, the best case scenario is that you find the number in one step. All right, so this would be the best case. The worst case is that you have the number that you're looking for is right at the end of the list, and you have to traverse the entire list before you get to it. And so the number of iterations required would be equal to n. Okay, so this is from the previous lectures. And we also looked at what's the average, but that's not relevant. So basically, the big O notation focuses on the worst case scenario for every algorithm. Okay, I hope that is clear. Any other questions?
So where did these equations came from?
So these equations, I've just given you examples, all right? So I'm saying if, for example, somehow somebody did all their calculations and so on, and they found out that the time is given by this equation, then what is the order of complexity of this? Okay, so I'm just pulling these equations out of a hat. Okay, and I'm just saying that if the complexity was given by these equations, then what would be the big O notation for it? Okay.
So can you explain the big O notation once again?
Okay, so I'm going to explain it the one last time, and then I would prefer that you can rewind the lecture once it's recorded. So basically, in the big O notation, you take, if you have an equation given for the expression, then what you do is you take the highest power of n. Okay, so in this case, the highest power of n is n to the power 4. This simply becomes order of n to the power 4. In this case, the highest power of n is n squared, so this becomes order of n squared, and you drop the lower terms. Okay, in this case, the highest power of n is n to the power 1, so this becomes order of n. Okay, it's fairly straightforward, kind of obvious concept, but we'll be using this quite often. So let's go on. Now let's take a look at a simple example. So for example, you had this Python program. Now you've already seen this iteration. So here what we're doing is for I is equal to, for I in range 0 to n. Now can somebody tell me what are the values that I will take in this case?
Mohammed Bilal.
Ji. Ji Bilal?
From 0 to n minus 1.
Right, so it'll take the values from 0 to n minus 1. And basically after it goes through the iterations, every time it's simply going to run this expression. Now this is not a very useful iteration, as you can see, because it's simply assigning x is equal to n repeatedly, okay? And I've just, I could have said x is equal to 0 here, but all I wanted to do is have an expression that's going to be repeatedly run every time this iteration goes through this loop, okay? So now the question is, how much time will it take? So it's kind of obvious, and I've actually plotted this, and this is a real world scenario. I've actually, if you want to look at the code for this, I can show you the code for this, but it basically what it does is it runs this expression for I is equal to 1 to n, and then there's some other things that we'll talk about later on. It looks at the time difference. So if I run this, for example, right now, you'll see that it's going to take a certain amount of time, and the amount of time is printed out. How it gets it, I'll talk about this later on, but basically it prints out the amount of time it took. So if I take a larger value of n, it will take a longer time. Okay. So what I've done now is I've plotted n for different values of n. I've plotted the amount of time that this algorithm takes to finish. Okay. And as you can see that as n becomes larger and larger, say 100 million to 200 million to 300 million, the amount of time taken is going from, let's say, 2 or 3 seconds all the way up to 15 or 20 seconds. Okay. But this equation is linear. Okay. So I hope you understand what linear equations are. I'm sure you've done this in your high school. So when it's a linear equation, clearly this is an order of n expression. Okay, so in the worst case, this will basically take n. The equation will probably be something like alpha n plus beta, where these are constants. Okay, so for example, it could be 20n plus 30, in which case, again, this is order of n. If it is also 100n plus 1000, and this number could be extremely large. So it could be, for example, 10 to the power 6. But since this is a constant, it will get dropped out. Okay, and this will again still be an order of n expression. Okay. Excuse me. So now let me ask you, can somebody tell me an example of an iteration which is an order of n squared algorithm? Okay, so this was an order of n.
Expression.
Can whoever is speaking up, please say your name.
Mohan.
Disha.
Sir, a quadratic expression.
Okay, give me an algorithm. So something like this, a Python algorithm. You've already seen this. Can you write a similar
Okay,
algorithm?
so
which
for
will take
I in range 0, n.
Yeah. Range
X equals to n squared.
Okay, very good. So and then you would say x is equal to n. Okay, so perfect. This will take n squared amount of time. Very good. Can somebody give me another way to do the same thing? So this is one algorithm. Any other ideas? An alternate way of doing an order of n squared algorithm?
Sir, Muhammad Shahzad.
Ji Shahzad.
So you can put another for loop inside this
Okay,
for loop.
very good, very good.
0 to n.
So that's a way that I've shown over here. So what you could do is, as was said earlier, you could either make this n squared, or what you could do is you could say for I in range 0 to n, and then you have another nested for loop. Okay, so this is what is referred to as a nested for loop. Okay, a nested for loop. Why? Because this loop is inside the other loop. And so what this is doing is using a different variable, j, and j is now in the range 0, n. Okay. So if you think about it, if you've got, let's say, a square, so this can be thought of a linear traversal going from 0 to n. But
Sir, may I ask a question?
Your name?
Zuhair Arif.
Ji, Zuhair.
Sir, अगर हम x is equal to n square कर दें instead of nesting the loop.
Okay, so that's an interesting question. So in this expression, if I change this to for x, sorry, not for, but if I simply change that to x is equal to n squared, can somebody tell me, will this expression now take linear time, or it will take order of n squared time? Order of n, or will it be order of n squared? The amount of time. Ji Bilal.
It will be n.
Order of n. Why?
Because it will only go from 0 to n minus 1, which will be approximately n steps.
So Bilal is right. So basically, the number of steps that will be taken will still be 0 to n minus 1. Okay. the constant over here will probably be bigger. In other words, for example, if it was earlier taking let's say 2n seconds, now it might actually take 4n seconds, right? So this constant associated with the amount of time might change. It might actually double. It might triple, because calculating x is equal to n squared will definitely take longer than assigning simply x is equal to n, because now you actually have to multiply these two things together, and that will take a longer time. But the number of steps is still proportional to n. So in other words, if you double n, the amount of time will not go up by 4. It will simply linearly increase in n. Okay, so just think about that. And I hope most people get it. So this will not change the order of n. It will simply still remain order of n. It will not become order of n squared. However, if you do a for loop, a nested for loop, then if you think about the square, okay, so it's actually going to go from 0 to n, right? And then this is where the I values are changing. Then it will set j is equal, initially I will be equal to 0. Okay, so for example, I is over here. Initially, I will be 0, and this will be j. Okay, so j will go from 0 to n minus 1. And then I will become 1. Okay, it will take on the next value. And then again, it will repeat for j is equal to 0 to n. Okay, then I will become 2. And then it will again go from j is equal to 0 to n, and so on until I becomes n minus 1. And then j will go from 0 to n minus 1. Okay, so this is how this loop will go. It's sort of like traversing a two-dimensional space. Okay, I hope that's somewhat clear to everybody.
So this is Maz Kareem. I have a question.
Yeah.
Sir, in the loop above, for I in range 0 till n, x is equal to n.
Yeah.
In practicality, how would this loop run? For example, would I put an actual value for n?
Yeah, so if you look at the actual algorithm, let me just show you the actual algorithm. So I've got some initial values. So what I'm doing is I'm setting n to be some value. So for example, I want n to be a very large value, so I'm taking n to the power, but just neglect all of that. But basically, I initialize n to some value, and then I simply run this. Okay, and then I'm using some things, the time, initial time, and the final time, and I print the difference. So for example, when n is equal to 20, the small n is 26, it takes 6 seconds. When the small n is 25, it will hopefully take a lot shorter time. Okay, it's taking 3 seconds. When n is equal to 23, it will take a shorter time. Okay, so that's how you practically run this. Okay, you're initially setting n to some value.
Oh.
Let's say n is equal to 10 to the power 5 or something, large values, and then you're running this. Is that clear?
So suppose in this loop over here, you set n is equal, capital N is equal to 10 to the power of 5.
Yeah.
Right, x is equal to 10 to the power of 5.
Yeah. So it'll simply do, it's simply going to assign x repeatedly 10 to the power 5 value. Okay, it's not very useful.
Oh, so it doesn't exactly do anything. Okay,
it's not doing anything. I could simply change this to be x is equal to 0. Okay, I just want to run some operation, okay, which is going to take some finite amount of time. If I don't have x equal to 0 or x equal to n, then nothing will happen. Okay, it won't actually run. There has to be something over here for it to be able to run for a constant amount of time. Okay, I hope that's clear.
Okay.
So now, if you've figured these two out, give me another example of order of n cube. Somebody else.
Sir, my name is Sarah Batul.
Yes, Sarah.
Sir, I think इसकी range जो है 0 to n cube.
Okay, so that's one thing. One way is to do this, to simply change this to n cube. What's another way to, sorry, not the first one, but simply to change this to n cube. But how would you do it in this fashion using a nested for loop?
सर इसमें हम एक और भी ऐड करेंगे for k in range 0 to n.
Okay, very good. So that's exactly what I've shown in the next slide. So here what I've shown you is that for I in range 0, n, and then for j in this range, and then for k, I'm using a third variable for k in 0, n. Okay, and I'm using some constant, x is equal to 0, for example. Okay, so earlier this was two-dimensional. Now what would this correspond to? A traversal of, this could be a traversal of a linear shape. This could be a traversal of a two-dimensional square. What would this correspond to? Any ideas?
Muhammad Bilal.
Ji Bilal?
It's a three-dimensional shape.
Yeah. So it will be simply a three-dimensional shape. So if you can see over here, I've shown you a Rubik's Cube, which is a three-dimensional. So basically what you're doing is you're going through all the blocks in this cube. Okay, so if, for example, you had a three-dimensional shape and you wanted to somehow traverse all of these individual blocks, then you would have, for example, I going over here, you could have J going over here, and you would have K going in the third dimension. This could be I, J, and K. Okay, so if you wanted to have a fourth dimensional, somehow if you can figure it out, if you have a four-dimensional space and you want to traverse all of that, then you would have a nested loop with four loops nested inside. So for I, for J, for K, for L, for example. Okay, and that would be order of n to the power 4. Okay, so I hope you get the general idea as to what is the complexity of an algorithm. G, name?
I'm Abdurrahman.
Ji
I
Abdurrahman.
want to ask that
Ji Abdurrahman. आपकी आवाज कट गई है. Can't hear you. I think you've muted your mic. Ji Abdurrahman. I think you're having
so this
problems.
algorithm represents number of dimensions.
Yes, so you could say that in a sense that this nested for loop is traversing a number of dimensions, and that also shows you the complexity of the algorithm. Okay, so this is if n becomes very large. Okay, so you can imagine that the number of if n, for example, is 1,000, then the number of blocks in this would be 1,000 times 1,000 times 1,000 would become 1,000 times the power of 3, which is 10 to the power 9. Okay, so that would be 10 to the power, so it would be a large number of blocks. Okay, so so basically this is indicating that complexity, that, and this is sort of at the heart of computer science. Okay, that basically in computer science, what you're trying to do is you're trying to write algorithms which are which ideally are linear in whatever that you're trying to do. Okay, so for example, if you have an algorithm which is counting, as I said, the previous example, that it's trying to find a number inside of an ordered list or an unordered list. Okay, so you're trying to find an algorithm which is very good, and by very good it means that it's not order of n cubed or order of n squared, it's order of n. Okay, so order of n would be preferred algorithm to order of n squared. Okay, so this is how you differentiate between a good algorithm and a bad algorithm. So you could have two algorithms which both give you the right answer, but if one algorithm is taking order of n squared time and the other algorithm is taking order of n, then clearly the order of n algorithm would be preferred. Okay, simply because order of n squared would become very large, which take a very long time very quickly. Okay, so so now let's take a look at some curves, and this shows you 5 algorithms, and I've shown these. I've not labeled them. An order of n squared, order of n cubed, order of log n, and order of n log n. Okay, so I haven't talked about these. I've already spoken about these 3 algorithms. And what I'm trying to show you is 5 curves, 1, 2, 3, 4, and 5. Okay. Now I want somebody to tell me which of these corresponds to which. For example, order of n. Does this correspond to the first curve, curve number 1? Or does this correspond to curve number 2 or 3 or 4 or 5? Which curve does the order of n correspond to? And somebody has
Sir, my name is Saira Batul,
G Sarah.
and I think yellow one shows ON because it is linear.
Okay, so yellow one, you're saying basically this corresponds to number 1.
Yes, sir.
Okay.
Sir Abdullah.
G Abdullah.
Sir, number 3.
So Abdullah is saying that it is number 3. So we've got Abdullah and number 3, and I think who was at number 1? Was it Saira? Okay.
Saira, yes.
Yeah. Any other suggestions?
Sir, number
Bilal.
2.
Bilal.
Number 2.
I need your name first.
Sir, Hamza, number
Mohammed
2.
Bil-
Hamza is saying number 2. So can people tell me how many people agree with Hamza versus Abdullah versus Saira? Or A, H, and S? I've got the names down.
Mohammed Bilal, number 2.
Number 2. Okay, so there are 2 people who are voting for number 2. So it seems like if democracy is
Tayyib
true,
Rashid.
G. Tayyib Rashid. Okay, so most people seem to be
Sir,
agreeing.
number 5.
Number Shahir is saying number
2.
Number 2 as well. Okay, so I think it's clear that the majority of people are with number 2, and in fact that is correct. Well, let's see why it's correct. Well, as you can see that it's very simple. 8 corresponds to the number 8 over here, roughly. Okay, and you can see that this is a straight line. All right. Now 1 is kind of confusing, but if you can see that number 1 is slightly sloping down. So it's not really going linearly. So this is not really linear. This is essentially linear. And it's a little confusing, but number 2 is the correct answer. Why is number 3, 4, and 5 clearly not the correct answers? Because as you can see, they are sloping upwards. Okay, they're going upwards. And of course, number 5 is very sharply going upwards, but even number 3, you can see that it is not really straight line. If you put a straight ruler, you would see that it is actually not going straight. Okay, so this is correct. Now let's look at order of n squared. Now, can people tell me which one is the right answer for this? 1, 2, 3. Well, number 2 is already gone. 3, 4, or 5. Shares there, yeah.
Sir, this is number 4.
Number 4. Okay, that Zia is not saying number 4.
Shahir Sabri.
Sabri, Ji Shahir.
I think it's 4.
Number 4 again.
Tayyib Rashid.
And who's that?
Sir, 4.
Tayyib Rashid, 4. Okay, so most of you are agreeing on number 4. And can somebody explain why they've chosen number 4?
Sir, because Shahir Sabri.
I didn't get your name.
Shahir Sabri.
Ji Shahir.
Sir, because the slope is increasing as a power, it's exponentially increasing.
I think this is basically what you're saying is that you can simply see that 5 squared is actually 25. Right? And 5, this is linear. Can you please turn your mic off? Okay. You can see that 5 and 5 were linear. 6 and 6 were linear. This was clearly linear. And number 4 is clearly the quadratic expression, the order of n squared. 5 is going to 25 and 4 is going to 16 and so on. Okay. So this is order of n squared. Order of n is over here. Okay. Now let's guess the rest of it, order of n cube. I think that should be fairly straightforward. 3 is going, n cube is around 27. 3 times 3 times 3 is 27. So this is clearly order of n cube. So I'm going to remove some of these and simplify this. So this is order of n cube. This is order of n squared and order of n. Okay, now we have these two, which clearly must be the other two. So which do you think is order of log n and which one is order of n log n? Ji Shahid.
Number 3 would be log n.
Order of?
And number 1, order of log n.
You're saying this
and
is... Okay, so you're saying number
number 3 is order of log n.
Order of log n. Okay, Shahir is saying this. Do people agree or disagree with Shahir?
Number 1.
Disagree.
Okay, so I think people are disagreeing. People are saying that order of log n should be number 1, and which basically means order of n log n is this one, number 3 over here. Okay, so that's the final result, and I'll show you the actual data. So basically, order of n is over here. Okay, order of n squared and order of n cubed. These were the obvious ones. Now, order of log n is actually better than which algorithm would be preferred, order of n or order of log n? So if you look at order of log n, as n goes to 2 or 3, or log n is even smaller than n. So as n goes up to 8, log of n is only 3, and this is basically logged to the base of 2 of n. Okay, so 2 to the power 3 is 8, and that's why you can see that this number over here is simply equal to 3. All right. Now, if you have n times log n, that's larger, because what you're doing is you're taking 3 and you're multiplying it with 8, so you have 8 times 24, and so that is why order of n log n is a little higher. Okay, so basically what you can see is that if you're using log n, it's actually better algorithm than n, and n log n is worse than n, but it's better than n squared. Okay, so this gives you the different types of algorithms that one could have, and that not all algorithms are going to be the same. Each one of them, the complexity is sometimes easy to determine, as we did in the previous examples, but sometimes it's very difficult to determine, and you need to do a lot of mathematical guesswork or calculations before you can actually determine the complexity of an algorithm. Okay, so any questions up to this stage? Okay, if not, let's go on. Now, this was the earlier algorithm, which was the unsorted number search. Okay, so this was example from the previous lectures where we had an unsorted list, and we were saying this was the length of the list, and we were basically saying that, let's say if we wanted to search for a number x, and if we did a linear search, this was a linear search. We started with I is equal to 0. We said, is this number the number that we're looking for, the number 5? No, then we would go to the next number, and so on, and eventually we would find the number if it was in the list. Okay, and we said that this had a complexity of order of n. Okay, now my question to you is, can we improve this algorithm? And if we wanted to improve this algorithm, which algorithm could actually be better than this?
Sorted algorithm.
Okay, and how? And so if we and again, I didn't hear your name. Okay, so somebody, a nameless person, said a sorted algorithm. All right, and if I can ask the same person, what do you think the complexity would result as? So it's going to be better. It clearly has to be better than order of log n. Anybody else willing to answer that?
Log n.
Log n. Clearly, well, it doesn't have to be order of log n, but this could be, if it is order of log n, then clearly we've got a better algorithm. Okay. But now the challenge is that what is being suggested is that somehow we have a list which is sorted. Okay, so that was the trick part, is that somehow we can convert this into a sorted list. Okay, so how do we do that is a topic for another lecture, but let's assume that somehow we've got the sorted. So what would the sorted list look like? It would be 3, 4, 5, 6, 10, and 20 and 25, right? So let's just assume that we have this sorted list. Now the question is, if we do have this as a sorted list, how would you actually improve your algorithm? So let's go back to this algorithm and say, how would we change this algorithm so that we can actually sort it and we can actually search for it in a faster manner, in an order of log n manner, let's say. Okay, so the people who said have a sorted list, can you try to give an answer? So why do you think it's, and what would the actual algorithm be? Any thoughts?
So marketing, but I'm not from 5778.
Okay, that's okay.
We could keep splitting the list in half and check the number behind and the number in front.
Very good, very good. So how would you start it off? So let's say we've got this list and we want to write the algorithm. So we want to, basically what you're saying is somehow we split this list. So where would you start off searching? What would be, so let's say you start, what would be your initial value of I? Where would you search in this list? Somebody who doesn't have a mic problem. Turn your speakers down before you turn the mic on, or put on a headset. That's the ideal thing. Anyway, somebody else?
Muhammad Bilal.
Ji Bilal.
We could start at n equals to 3.
Okay, very good. So what you could do is you could start searching over here, because you can see that there are 1, 2, 3, 4, 5, 6, 7, n is equal to 7. So we somehow divide, we look in the middle. Okay, so you've got n is equal to 3. Forgetting about the, roughly, but let's say you start off in the middle. And so how would you compare? What would your first comparison point be? We start at, let's say, I is equal to n upon 2 approximately. Okay, then what would your comparison point be?
So we will check that is the value greater than the search value or not.
Okay, well, first of all, you would actually do a check whether this is the answer. Okay, so suppose that you're looking for the number 6, and it so happens that this is the number, so you'd obviously get an answer. Okay, so so what you would do is, let's say you set I is equal to n upon 2, all right, and you search for whether the middle number is actually the number that you're looking for. If that is true, if list sub 3 is equal to the number 6 that you're looking for, and if it's yes, then you're done. Okay, but now if that is not true, then what do we do? Okay, so some of the suggestions that were coming earlier, now let's put those over here. So somebody said that we could do a comparison. Gmaz.
Yes, we could check if the number at that point in the index is greater than 7 or smaller than 7.
Okay, so let's say we check is L sub I greater than X. Okay, so let's say we're looking for the number 10. Okay, and we check whether L sub I, let's say, is less than X. Okay, we could do either one. But if it is less than X, then what do we want to do? So in this case, 6 is clearly less than 10. So what do you want to search now? I think that's Sohaib, but I think you're having internet problems. Somebody else?
No, sir. I was saying we will cut off.
Somebody else? I think you're having problems with the internet.
So, Farhan.
Ji, Farhan.
Sir, in this case, we go to move towards the right side and search for it.
Yeah, exactly. So if the number 6 is less than the number 10 that you're looking for, then basically you're going to search for the top half. Okay. So you could say if L sub I is less than X, search top half. How we do that? We'll have to figure it out. Okay. So we'll search over here. And if this is a yes, if this is a no, then what are we going to do? Search the bottom.
If it's equal, then we just
if it's equal, we've already done that. If it's equal to the number, then we've got the result. Okay, so for example, if this happened to be 10 or then we would actually have the result. So we'd stop immediately. But if it is not equal to, then we search for whether it is less than, and if it is less than, then we search for the top half. Okay, and if not, then we search for the bottom half. Okay, then we search for this portion. Is that clear to everybody? Okay, so basically there would be.
I have a question about
start. G.
So you wrote I is equal to n upon 2.
Yeah.
Since I starts 0, aren't we supposed to take n?
Okay, so good point. I'm sort of ignoring the boundary conditions. I'm ignoring details. Okay, so the reason, so I can say approximately I is approximately equal to n upon 2. In fact, you would have to take, because n could be an odd number, so n upon 2 will, so in practice what you would do is that I is equal to n upon 2, and you would either take the floor of that number or you would take the ceiling of that number. Okay, this would result, if you know your math operators, this would either result, this would be the floor or this would be the ceiling. Okay, so if this is, for example, n is equal to 7, this would be 3.5, and you would go to the number 3 over here. If you go to the ceiling, this would go to the number 4. Okay, so if you took the floor, you would go to 0, 1, 2, 3. This would be the more appropriate thing. If you took the ceiling, you would end up over here. Okay, but those are details that we can roughly ignore. When you're actually implementing this algorithm, you'll have to worry about those. But at a high level, you can simply write it roughly as n upon 2, okay, approximately. But that's a good point. It's a good question. Okay. So now the next question is, how do we search the top half, or how do you search the bottom half? Okay.
We can just repeat the same process again.
Say that again. I didn't quite get you. Gmas.
We could repeat the same process again.
Exactly.
Dividing the list in
exactly.
half.
So now what we're going to do is somehow we're going to, if we're looking for the top half, we're going to now make this the entire list. Okay. And we now focus on getting the middle portion of this. How we do that, it's a little tricky. And I'm not going to show you the algorithm right away, but basically you get the high level concept that you're going to look at the middle portion over here. If you're searching the bottom over here, you'll make this the list, and you'll search and you'll make, and you now the new value of I will be over here. Okay, so the new value of I will be over here, or the new value of I will be over here. Okay, so you'll have to adjust those variables so that you go through the appropriate portion. And now you'll have to actually search this portion of the list, or this portion. Okay, so you won't go through the entire list, but you'll actually halve the list, and you'll actually only spend half as much amount of time. Okay, So if you've understood this, now let's take a look at this and see as n is small, n is equal to 1, so you simply have one number. What is the maximum amount of iterations? Well, clearly it's going to be 1, okay? Because n is equal to 1, and if you're going through that list, clearly you're either going to find it or you're not, and you immediately have the result, okay? Now, as n becomes 2, what's the maximum number of iterations? So let's say you start off over here with the yellow line. We're taking the lower portion. So what's the maximum iterations that would have over here? Any suggestions?
We want either be the floor or the.
Okay, so if you had one iteration over here, what's the worst case when you have the list is of 2?
Two.
It would be 2. Can you explain that?
Because the maximum number of objects in the list are 2.
Okay, so yeah, so I guess you could start with number 3, and if it's not number 3, then clearly it's the other one. So it's kind of obvious, and the linear search would do just as well. Okay, so let's see what happens when it becomes bigger. Okay, now the list is doubled. I'm keep doubling the list. Now, how many iterations? What's the maximum iterations will it take? Any thoughts?
Three.
Okay, 3, and I didn't get your name.
Muhammad Bilal.
Yeah, Bilal. Can you explain why you said 3?
So it will be either 5 or 4. So if it's not 5 or 4, then either it will be greater than or lesser than. Then we're going to half the list again.
Yeah.
So from 5 or 6, then from 5 or 6 it will be halved again to either one of these two.
Yeah. Okay. So basically, let's say if you started with 4 as the middle point, then and if you're looking for, let's say, the number 6, it would then go over here, okay, and it would search the top half, and then it would again, if it wasn't this wasn't the number that you're looking for, then it would go over here. Okay, well, it's still not clear how the algorithm is operating. Let's take a look at this case where it has length of 8. Okay, so now how many operations? What's the maximum iterations? Ji, Bashir. Sorry, who is that?
5, sir.
Ji, go ahead. Name? You always need to tell me your name first.
Tayyib Rashid, sir.
Ji, Tayyib Rashid. So it will be.
Sir, 5 iterations.
5. Okay. Any other thoughts? Does anybody agree or disagree? Okay, let's try it out. So let's say we start off in the middle. So let's say this is the middle, and the middle could be the 6 or 10, but let's say 6 is the middle. Okay, and let's say we're looking for the number 26. Okay, so number 26 is greater than 6. So now we're going to look at the top half. Okay, so then we're going to look at the middle of the top half. So this was the first step. The second step is we're going to look at number 20. Okay, this number 20, 26 is still less than 20. So now it's going to look at the top half of this. Okay, so it's going to go over here. This will be the third step. And we look at number 25. If 26 is still greater than 25, now it will again look at the top half. And in the fourth step, it will find it. Okay, so my guess is that it's going to be no more than 4 steps. And can anybody give me an example where it will be more than 4 steps? Okay, so think through it. It will never be more than 4 steps. Okay, so 5 is not the right answer. It's going to be 4. Okay, now let's look at an even bigger number. So let's look at 16. So this is n is equal to 16. And now let's take a look. What's the worst case over here? What do you think is going to be the answer over here?
Mohammed Bilal.
Bilal.
I think it should be 5.
Okay, so 5 should be the right answer, and you've got some idea. You can see that it's going from 1 to 2, and then from 2 to 3, and 3 to 4, and 4 to 5. It's not going linearly. Okay, so let's take a look at 5. Why is it 5? So we start off, let's say the number that we're looking for is one of the extremes. Okay, let's assume that the number that we're looking for is, let's say, 31. Okay, so we start off at 26, which is roughly in the middle. Okay, and we'll say, well, is 31 bigger than 26? We say yes, so we're going to look at the top half. Okay, in the top half, let's say we look at number 66. We say, is 66 less than or greater than 31? Well, 31 is on the left side, so now we're going to look over here. Okay, so how many steps have we done so far? This was the first step, this was the second step, and now we're going to go to the third step. Okay, so now we're going to look over here, and we look at number 38. So this is the third step. The third step says that it is still 31 is smaller than this, and now we're going to get it in the fourth step. So this was an example where we actually got it in 4 steps. Okay, but if you look at another example, 82, my conjecture is that it might actually take 5 steps. Okay, and you can let's try it again. So you start off at 26, then you go to 66. 82 is still greater than 66, so you look over here. This was the second step. Now you look over here. This is the third step, and you look over here. This is the fourth step, and this would be the fifth step. Okay, so work this out on your own. Look at some examples, and what you'll see that, and this is what is referred to as a binary search. Okay, so the binary search is basically what it's doing is taking the list and is dividing it up into halves. Each time it looks at the list, it converts it into half the length. Okay, and so now the question is that the number of iterations that is clearly not linear. Okay, so can somebody tell me now, if it is not linear, what is it? Which one does it seem to be? Is it better than linear? Is it worse than linear?
Mohammed Bilal.
Bilal.
I think it's log n.
It seems to be log n. Okay.
Yes, log n. It's better than n.
And why is it log n? Can you explain why do you think it's log n?
Because n is greatly increasing, like it's doubling, but the max time to iterate through it is almost constant or constantly increasing by 1.
Yeah. So your intuition tells you that it's actually log n, which is the correct answer. So let's take a look at this. What's the best case scenario for this binary search? What we just described is called a binary search, okay? Because it's dividing it up into 2. So that's where the binary number comes in. So what's the best case scenario? How many steps will it take?
I guess the best case, Mohammed Bilal, best case would be 1 if it's exactly in the middle.
Yeah. And what's the worst case?
Worst case would be log n.
Yeah, so it will be roughly
if it's at the extreme.
Log of n, but it also depends on what log you're taking. If you take log to the base of 2, so I'll show you the actual number. It's actually log n plus 1. Okay, so for 32, log of 32 to the base 2 is actually 5, and this is 6, so it's actually the log of 1 is actually 0, so it's 0 plus 1. Log of 2 is 1, 1 plus 1, and so on. So you can see that the answer is actually log of n plus 1. Okay. Now, if the equation is log of n plus 1, then what is the order of the algorithm? What do we do with the constants? As n goes to
Muhammad
infinity,
Bilal.
G. I would appreciate if somebody else can also try to answer. Don't want just one person.
Log n plus n.
Sorry?
Can it be log n plus 10 or log 10n?
Name, please. Ji Umar.
Because 1 is log 10 base power 10. So we can multiply it to log 10n.
Okay, so remember my initial discussion about what do we do when we have, how do we determine whether something is of what order? Okay, so we take the highest power of n. Anything that's a constant, we drop. Okay, so the highest power of n over here is log of n. Okay, so because log of n is the highest power of n, we're going to drop this constant, and this will become the order, the big O notation would simply be order of log of n. Okay, I hope that's clear to people. Any questions? All right, so now you can see that this algorithm is actually superior simply because of the way it's operating. However, what have we actually sidestepped? When we went from the linear algorithm to a sorted algorithm, where did we sort of do something which was, we sort of hid the complexity somewhere? Can somebody tell me where we've actually hidden the complexity? So it's become better, right? But has it become without any cost, or is there a hidden cost somewhere?
So Shazib, sure.
So
it is extremely complicated to sort this list.
Yes, very good. So actually, the cost is hidden in the fact that we said that somehow we made a big assumption. Okay, sometimes you say that assume is not a very good word. Okay, so we've assumed that we have an ordered list, but how did we get the ordered list? Okay, so that's a something that we look at in another lecture, but that's where the complexity is hidden. So if somehow we can get the ordered list, then we can reduce the complexity of this algorithm from linear to log n. Okay, but how do we get the ordered list in the first place is something that we'll take a look at as we go further in this course.